our discussion of what direction these vectors need to have and which quantities here on the board are in fact vectors is complicated by the fact that the velocity of this point at the edge of the blade isn't constant. It has the same magnitude all the time, but its direction changes constantly. When the point at the edge of the fan blade is here, it's moving that way, tangent to the circle in the direction of motion. And when that point is here, it's moving this way. And when that point is here, it's moving that way. So the velocity at all times is changing direction. And if r is to be some kind of like radius vector, some sort of position vector relative to the axis around which we're rotating, it's also changing direction, but in a completely other, perpendicular to this one. That the radius moves, or the radius has that direction and then that direction, and I guess they are always perpendicular to each other. But how are we supposed to reconcile that in one equation? The left-hand side is in a completely different direction, perpendicular to this direction, if it is a direction. Well, wait a minute, it has to be a direction. If only one of these vectors, I'm sorry, if only one of these variables is a vector, then we're stuck, we're screwed. The left-hand side is a vector that changes direction, right? That's we need. If this equal sign is going to work, then we need the right-hand side to be a vector that changes direction. If r is scalar and omega is the vector, the angular velocity is the vector on the right-hand side, what we liked about the fan, about this description of angular motion, is that it's the same for all the points and for all, it put on a certain setting and the speed with which it rotates is the same. The angular speed with which it rotates is the same, whether we look now or later or whatever. So the direction of omega, if it is a vector, shouldn't change. Never mind, I'm not sure what direction that is, but it shouldn't change because the rotation doesn't change. But now we've got a right-hand side that doesn't change and a left-hand side that does, so we can't do that. What if omega is scalar and r is the vector, but they point in different directions? Then the direction of the right-hand side isn't the same as the direction of the left-hand side, so this is a broken equation. The only way to make this work is if all three are vectors. It's the only way to do it. It's the only way to relate a changing radius, a changing direction radius, and a changing direction velocity. There's got to be another vector. There has to be some kind of vector algebra going on here. And we already know what kind of vector algebra this is. If we are going to be multiplying two vectors and ending up with a third vector, that's the kind of product that is the cross product. I wondered why we defined it originally. Now, I still have no idea what direction omega points in. It doesn't really make sense that it has a direction at all. It's talking about angle, right? But we have to. We have no choice. So this jar lid from the previous segment makes a triumphant return. If we've got this jar lid, and I would like it to rotate in the plane of the whiteboard about that point. Sorry, you can't see because my hand's in the way. About that point right there. I can hold it there with this pencil. And then, let's see if I can do this without blocking your view here. And then I can cause it to rotate around that point. Causing a thing to rotate in a plane like the blades of the fan do requires an axis of rotation perpendicular to that plane. So if the angular orientation is to change, that's due to a rotation. And it's due to a rotation about which axis? The axis relative to which we define the rotation. That's the direction of the rotation. That's the vector direction that indicates the plane in which we're going to rotate. Let me say that again. The pencil pointing out of the board back at the camera, that's the axis around which I want the lid to rotate. And I end up with a rotation perpendicular to the axis of the pencil. That's what we're talking about. So the pencil then represents the direction of the rotation. It's as good a thing as anything else. If we're going to rotate around this axis, then theta is going to rotate. If we talk about this point here, that we can rotate that point from 0 radians to pi over 2 radians to pi radians around to 2 pi radians. 2 pi radians measured relative to an axis through a coordinate system set up with an origin at this axis. That 2D coordinate system is perpendicular to this axis, and this axis tells us what we're going to measure angles with respect to. That's the direction of omega. We've got an explicitly three-dimensional thing going on here. Okay, cross products, remember, multiply according to the right-hand rule. We orient our fingers of our right hand in the direction of the first part of the product, and then bend our fingers so they point, without breaking our knuckles, so they point in the direction of the second part of the product. The thumb of your right hand then points in the direction of the result. Does this work? All right. So we start with our fingers pointed in the direction of omega, which I said was back at the camera. Okay. omega points out of the board. I'm going to look at this point here. If we relate omega, r, and v, it should work. Omega points out of the board. Omega cross into r. My fingers have to bend this way, and then my thumb points in the direction of the velocity. Start with your fingers pointing away from the board. Then I curl my fingers so that they point in the direction of the radius vector. My thumb points up and to the right, which is the direction of the velocity vector, the linear velocity vector. One more try. Start with my fingers pointing out of the board. Curl my hands so that my fingers point along the radius vector. My thumb points in the left direction. Yeah, it's got it. All right, it works. It works as long as we are actually rotating counterclockwise. Because then the answers are backwards. So I need to adjust my definition of omega. It's not just the axis, it's which direction. And it's which direction according to the right-hand rule. If you take your right hand and curl your fingers around in the direction of the rotation itself, then your thumb points in the direction of omega. Again, a right-hand rule. So we curl our fingers in the direction of the rotation, start at your first knuckle and proceed out towards your fingertips. That direction, your thumb points out. If we turn the fan around, then the blades rotate the other way. They rotate clockwise. And if we do that with our hand, our thumb points into the whiteboard. In the X, Y, Z, in the negative Z direction if we're going clockwise. If we're going to talk about rotation in an XY plane, and I think there's no reason that we shouldn't talk about rotation always in the XY plane, because we can always draw the coordinate system however we need to so that it works out that way. If we're going to talk about rotation in the XY plane, clockwise rotation, that gets us a thumb, an omega, that points in the negative Z direction. Counterclockwise rotation gets us an omega that points in the positive Z direction. We are used to defining counterclockwise rotations as positive angles, and we ended up with an angle in the positive, with an omega in the positive Z direction. It's meant to be. It's meant to be. So, all right, omega has a direction according to the right-hand rule. Curl our fingers, and our thumb points in the direction of omega. If counterclockwise, it has the direction of k hat in the Z direction, as long as we're drawing our axis X, Y. Z points out of the board back at the camera. If we're talking about clockwise rotation, we've got the opposite. Ooh. Okay. Man, cannot hold anything. Now that we've talked about directions, if omega changes, if we speed up or slow down our rotation, that doesn't affect the direction, so we just change the magnitude of omega. Well, maybe we turn around and rotate the other way, but we're still along one axis. So alpha points in the same direction as omega. R points in the same direction as R. This is, again, a cross product. And we're going to end up with a vector that is tangent to the circle, just like the linear velocity vector was tangent to the circle. So I'm just going to call this tangential, because we know that if motion is occurring in a circle, that there is centripetal acceleration as well. This is not centripetal, it's not radial, it has very little to do with that. This is the acceleration around the circular path associated with the fact that we might be speeding up or slowing down our rotation. So I have acceleration tangent to the circular path of the point in question, the point r away from the axis around which we're rotating. Cool. Next segment.